Right, so I want to just come back a little bit about what we talked about yesterday, because it was maybe a little bit quick towards the end. So remember, so that was sort of the philosophy of the thing we want to do, was to say, well, what we really want to understand is somehow this solution map, right? So that was essentially, here you have some realization of some driving noise. Here you have somehow the right-hand side of some stochastic partial differential equation. And here you have a solution map that takes your noise and takes the equation you're considering and solves it and gives you some, say, continuous function. And we want to understand how this map behaves when you turn this sort of nice regularized noise into actual white noise, or some other kind of singular noise. And the way we do this is that first we build this space M, which contains some additional information about the noise. And in the example, we've seen this example of this 542 equation, where this was essentially consisting of the solution to the linearized equation and then its square and its cube. And then we build a solution map that takes that data and spits out some solution. And this one I draw it in green because it somehow has much nicer properties than the one which, well, this is supposed to be red, but there's no red chalk. So the red one is basically discontinuous in sort of the natural topology you would want to put in here so that white noise actually belongs to your space. Whereas if you choose this space here correctly, then we can actually make that map here continuous in the suitable kind of topologies. So in the example that I gave you, up here you had somehow v square v cube, and you put some kind of C alpha topology for some negative but not too negative alpha, and then we saw that the solution map, well, at least we argued somehow that the solution map would actually be continuous. And then what happened is that if you just naively take your noise, solve the linearized equation, and then take the square and the cube, well, then typically those fail to converge because the square actually blows up. So there was a logarithmic divergency there. And so what you have to do is you have to subtract suitable large constants. And if you choose these constants in the right way, so in this case for the square you would have to subtract its expectation. If you choose this in the right way, then you can actually make it converge. Okay, and so here we encode this in some group that acts on this space. And what you want to do is you want to find a sequence of group elements here which depends on epsilon, so that when you take your epsilon regularized noise, you put it up here, and then you act with the epsilon element of your group. Then this converges to a limit, so that then you also get a limit here just by continuity of that solution map, right? And then what we've seen also in that example is that the same group acts in a sort of dual way, if you want, on the space of right-hand sides of the equation, in such a way that if you fix formally the form of your right-hand side here, you take your noise here, you lift the noise, and then you act with a group element, you look at this solution, then that's the same as actually solving the original equation in the usual sense, but with a different right-hand side, with the right-hand side obtained by this dual action of this group on the right-hand side, okay? And so now there are basically three problems to somehow implement this in general, right? So there's one problem which is basically algebra, and that somehow understand the structure of M of this group R and its action on M and the space of right-hand side. Okay, so this is somehow a purely algebraic question. It's sort of a structural question. And the reason why I put the space M in here is because the example that we saw, M was just a linear space. It was just C alpha times C alpha times C alpha. But in general, actually, M will not be a linear space. So it will be a non-linear space, and then you have to actually understand a little bit the structure of this space. So then there is an analysis question, which is to show that the green arrow, where's the green chalk? Okay. Show that the green arrow is continuous. And then there's a probability question, which is, well, show that one can find elements, say, G epsilon in your R, such that if you lift, so that somehow G epsilon, well, let me give a name to this. So let me write psi for the map that just takes the noise and lifts it to this space, so that this converges. And here you would want to show not just that it converges for some way of regularizing the noise. You want to also show that the limit that you get is sort of universal in the sense that it doesn't depend on how you approximate your noise by some smoother versions. Okay. So maybe let me just give a few references. I mean, this story, so at least this philosophy was actually first put forward by Terry Lyons in the context of just usual stochastic differential equations. And that led to what's called now the theory of rough paths. And so the picture in the theory of rough path is somehow basically the same. And this space would be what's called the space of rough paths. The only difference is that in the case of usual stochastic differential equations, there's no renormalization needed. So these bits don't exist in that theory. And then there's also been some recent work on this kind of topic, and there have been several approaches that were developed. In particular, there's an approach by Gubinelli, and there's also an approach by Antti Kupiainen. And in some sense, it's also somewhat the same philosophy. What changes is mostly the analysis part in these different approaches. Okay, so somehow in some sense, the definition of this space is somewhat different in the different approaches, and therefore the analytical techniques used to build this map and to show that this map is continuous are slightly different in the different approaches. The algebra part is also, well, so in the approach by Gubinelli, some says at the moment, it only allows to deal with situations that are somewhat simpler than the general situation. And in these simpler situations, the algebra part becomes somewhat trivial. And so that's why one doesn't really see it in his work, even if it's somewhat hidden. And the same in the work of Kupiainen, actually. So the algebra part is somewhat hidden because it's a little bit trivial for the examples that it can treat. And the probability part is completely identical in all of these works. Sort of the things that you need to show, the ingredients that you need to show are really completely equivalent. And the actual objects you end up building, the actual solutions you end up building in the end are the same in all cases, as they have to be, because they are supposed to be somewhat universal objects. If you ended up with different objects, there would be something wrong, right? And right, and so in the general case, so somehow the analysis part was sort of well understood in sort of the paper that I wrote, which is now maybe, I don't know, 4 years old or so. So that does somehow completely settles the analysis part in a quite general framework. Part of the algebra part was also settled in that paper, so the structure of M was completely settled in that paper. But somehow this group R was only characterized in a very indirect way. And the action on F was also only just checked on specific examples and wasn't really well understood. And also the probability part was somehow done in specific examples, but also not really well understood in the general case. And so now we have, so there are 2 recent papers. So one is a recent preprint, which is joint work with Lorenzo Zambotti and Ivan Brunet. And in that work, we sort of settle completely the correct question of somehow understanding this group R and its action on the space M up there. And there's a separate paper which is actually not yet on the archive, but which is almost finished, which is joint with also Ivan Brunet, AJ Chandra, and Ilya Shevirev. And there we show somehow the action, this dual action of this group R, the same group R, on the space of right-hand sides of the equation in a kind of very general context. And there's another very recent paper with AJ Chandra where we completely settle this probability question in a general context. So we show that under somehow very weak assumptions, it works basically well. Okay, so there is this subcriticality conditions I mentioned yesterday. So this one is really necessary for this whole machinery to work. And in the paper with AJ, we show that, so say, for example, if your driving noise is white noise, then as soon as you have the subcriticality condition, this always goes through. In situations where the noise is more singular than white noise, there are additional conditions that need to be satisfied. And so sometimes, and if these additional conditions are not satisfied, there's really something else happening. So again, it's not just that we don't know how to prove things, it's really that things behave differently. So it's actually, so there's this subcriticality condition, and then in some situations there are some additional conditions that need to be satisfied. Okay, so now yesterday, yes?
To implement this equation with kicks with usual like Dirac masses that would introduce discontinuities?
You can do, right. Kicks are not very nicely behaved, yeah. So kicks tend to not satisfy the analytical conditions that we have. Yeah. And you also, yeah, so I mean, so kicks are bad for this theory, and also heavy tails are bad, right? So we need things to be light-tailed because here we control things via controls of the cumulants. And so in particular, you need all the cumulants. And you need all the cumulants to behave somehow in the way you would expect them to behave from naive power counting. Right? So you're not allowed to have so strange behavior in some of the higher order cumulants. Yeah. Okay, so yesterday, I mean, I gave you a bit of sort of some hints of what this space M looks like, but so I want to just come back to that and sort of explain a little bit more how you build this space M. So sort of construction of M. And I'm going to focus to the case of this geometric stochastic heat equation, right, which was this dth equal dx square h alpha alpha equal to some Christoph plus some Christoffel symbols dxh beta dxh gamma plus sigma I alpha psi I, right? So that was this equation that we looked at yesterday and the day before. And so we saw that at least formally, when you want to understand the local behavior of solutions to this equation, then you had a bunch of processes showing up, and it was convenient to encode them with these little, tree-like pictures like this, right, where each of these guys represent one of the noises. So in principle, of course, since here you have more than one component, you would also have to sort of specify which one of the components this is. And then these wiggly lines represent convolution with the derivative of the heat kernel. And the straight lines here represent convolution with the heat kernel, right? So here, for example, for this picture, we would want to, right, so we have this map, boldface pi, that turns a little picture into an actual process. And so this picture here would represent something like, well, you take the derivative of the heat kernel, you convolve it with one of the xi's, so say you have an I here and a j. Right, so you convolve with psi I, that gives you this bit. Then you multiply this by the heat kernel convolved with psi j. That gives you this one. You multiply them because these two are joined together here. And then you take this product and you convolve it with the heat kernel, right? So in some sense, this little picture here is just a shorthand notation for this process. But it's convenient to view this not as a process, but just as a picture, so just as a sort of combinatorial object, because then that gives us the freedom to actually slightly change the definition. Right? So this map here that turns the picture into the actual process that the picture is supposed to represent, we want to allow ourselves to actually change the definition of that map, and that's precisely what that group up there is going to do, right? So if we want to interpret this as meaning this, but we want to allow ourselves to actually change the meaning of this product here, right? And so that's what this map here is going to do.
So this map, the pi is indexed by element of R.
So no, so the pi, right? So R, I haven't really said what it is yet, right? So what we have is now we have a collection of these little objects. And so we have a vector space, which is just a finite dimensional vector space, which is just the linear span of all these things, right? So there was somehow the 1, there was the x that we needed, then there's somehow the psi itself, then there's the psi itself, but with this. Then there are things like that, maybe. Sort of all the pictures that appeared in this expansion yesterday, and the similar pictures that would appear in the expansion for the right-hand side of the equation. Okay, so you just view you view it as a purely combinatorial thing, and then you just look at the vector space with basis elements.
Until the
given.
degree is less than something, right?
Right, so now each of these guys comes with a degree, right? So the degree of this guy would be 0, the degree of this guy would be 1, the degree of this guy would be basically minus 3/2, and then taking a convolution with a heat kernel increases by 2, so this would be 1/2. This would be minus 1, right? Because taking convolution with derivative of heat kernel increases by 1. So each one of these guys would be minus 1/2, and you have 2 of them, and the degree of a product is sum of the degrees. So this would have degree minus 1, etc. Right? So all of these guys have a degree, and the subcriticality condition is precisely what guarantees that if you look at the degrees of all the little objects that appear in your expansion, these degrees are sort of bounded from below, and they tend to increase. Okay, in the sense that if you fix any fixed value, there's only going to be finitely many that have degree less than that value. Okay, so the degrees sort of increase in the same way as for the usual polynomials, right? And then yes, so as Nicola said, you might want to stop somewhere, or if you want, you can just keep all of them, and then we're just going to look at linear combinations that actually stop somewhere. So it doesn't really matter whether you stop or not here. And so now, okay, so we have this space T, which is just it's a basically finite dimensional vector space with some grading, which is not a usual integer grading, but it's sort of grading by kind of half integers that can be negative also. And now we also have remember, so what we saw yesterday is that we have this kind of recentering procedure, right? So we have this map, pi. So now pi, the boldface pi, is just a map. It's just a linear map from T into, say, distributions on Rd plus 1. Right? So the boldface pi just takes one of these guys and spits out a distribution or function. So for example, here it spits out the constant function. Here it spits out just the linear function x. Here it spits out xi. Here it spits out what I called v yesterday. Here it would spit out somehow, the derivative of v squared, etc., etc. Right? So, and then what we saw yesterday is that when you do these local expansions, you really don't want to do them in terms of this pi, but you want to do them in terms of some pi z's, which are some kind of recentered versions of pi, and they are recentered in such a way that near the point z, or say, I think I called it z naught yesterday, so that near the point z naught, they do actually have a behavior that sort of reflects their degree. Okay? And so the way we did this recentering is that we just, built a linear map which depends on the point z naught, which sort of shuffles these things around and which performs the recentering. So we can define these guys as being the boldface pi itself composed with some fz. And so the fz yesterday was the linear map that does the recentering, say fz naught, that does the recentering around the point z naught, right? So in the example that we had yesterday, so for example, fz naught of this guy here was something like the guy itself minus the value. So, well, let me write sort of v of z naught times 1. Right? So that's so that now if I apply the boldface pi to this, instead of just getting v of z, I get v of z minus v of z naught. And so it actually vanishes at the point z naught, and it has a behavior, well, it sort of vanishes at order given by the degree of this guy, which is a half. Right? And that just thanks to the fact that this guy is Hölder continuous with Hölder exponent a half. Right? So now these guys here, these fz's, I sort of quickly mentioned yesterday that they are basically uniquely determined.
Sorry, but
yes.
Once you apply the fz, and then it's clear that you can give a proper meaning when you apply pi, because the pi, the meaning we want to give to this little drawing, that's not clear a priori, but once you apply fz, that's a proper, well-defined meaning.
Well, not necessarily, no. So all these things are perfectly well defined as long as there's an epsilon, right? So as long as there's an epsilon, there's absolutely no problem, right? Now, this recentering here is not going to actually help with the problem of things diverging as epsilon goes to 0, right? So this fz has nothing to do with this, okay? So that's then a separate piece of the story. So at the moment, the fz is just there in order to recenter things in such a way that their behavior around a given point reflects the degree that we want to give them, right? And so that then, since we want to do something like Taylor expansions around that point, right? So what we did yesterday looks very much like a Taylor expansion, and we defined spaces that are very much like Hölder spaces, but replacing Taylor polynomial by these guys. And so then, well, you know, when you do a Taylor expansion around Z0, you always write things in terms of powers of Z minus Z0, right? And sort of the guy of degree k vanishes at order k at the point Z0, and that's sort of what the degree is supposed to mean, right? And so so this guy is really just there in order to give the notion of degree its proper meaning somehow. Okay. Okay, so so these FZ0s, they belong to, well, so there's actually a group G, and so the group G is just a group of linear maps from T to T that furthermore satisfy a few nice properties, right? And so this is the linear maps gamma, say, from T to T, such that, what? So there were a few nice properties that we wanted yesterday. So what were the properties that we wanted? Well, we wanted them so that on the, say, it doesn't change 1. So gamma 1 is 1. We wanted them to not change the noise itself. So gamma of the noise is just the noise. Then we said that on the x's, we wanted to just act, you know, it's like re-expanding a linear function around a different point. And so what it means is that, well, it just turns x into x, well, minus some constant times 1, right? And then we said, well, we wanted these gammas to be multiplicative, and that was this interpretation that if you multiply two Taylor expansions and then you re-expand at a point, it's the same as first re-expanding at that point and then multiplying them. And so I can write this as gamma of, say, AB equal to gamma A times gamma B. And the product here is the product of, if you want, joining these things by the root. Right? So there's a natural product here. This space is not really an algebra because we cannot multiply any two elements, right? So some products will not belong to this space, so it's not really an algebra, but it still has somehow a partial product defined on it. And so on this partial product, we want this identity to be true. And then the last identity we wanted was the way it acts on convolutions. And we said yesterday, well, basically it should commute with them modulo things that look like usual Taylor polynomials. Right? And so this, you can say, well, let me write here I of something is equal to I gamma A. I'll say minus this belongs to T bar, where here the map I is just the thing, you know, say I of a little picture is simply, you know, the thing convolved with the heat kernel, convolved with the derivative of the heat kernel. Okay, so you take a map, the map I is just the map that adds a convolution sort of at the bottom of your picture. And we want to have a property like this where the T bar is the span of just, you know, 1, x, x squared, etc. So that's just your usual Taylor polynomials. Okay, so that gives a, well, it's not too difficult to check that if you take two maps like that and you compose them, it gives you again a map like that. It's a little bit less trivial to check that the inverse of a map like that is also a map like that, but it turns out to be true, so this is actually a proof. Right? And so you want this F to be an element of that group. And so now we have basically a description of the space M. All right, so what is our space M? So now, well, definition if you want. So the space M consists of all pairs, if you want, boldface pi and F, such that the following is true. So the boldface pi, as we said, should be a map from, a linear map from T to D prime. The F should be just a map from RD plus 1 to G. Okay, so it's just a map that to every point associates an element of G. And then we want a few properties which sort of tell us that this can really be, that it's not unreasonable to represent, to sort of interpret this as being something like this, right? So what do we want? So we want, on the one hand, we want that pi of boldface pi of something like this is indeed, heat kernel convolved with boldface pi of that thing. Okay, so we want this line to really represent convolution with the heat kernel. Okay. Now, and the same thing for the wiggly line, which would be convolution with derivative of the heat kernel, right? And then what else do we want? Well, for the polynomials, we don't have any choice of what they are supposed to mean, right? And so we certainly want, pi of, say, x or x times something, right? So we want this to be the map, well, I don't know how I should say, so the identity map, right? So if the map z goes to z times, or actually, so if say here I have xi, so it would go to the ith component times this, right? And this is well defined for every, right? Multiplying by a smooth function is well defined for every distribution, right? So this always makes sense. There's no problem in defining that. And then the other thing that we want is we want the degree, right? So we want the behavior at every point sort of z to really be reflected in the degree. Okay, so that's very, very important. And so we want that if we define, right, so we define pi z like this. Okay, so now we have a map. We have a map F. F is a map from RD plus 1 to G. So for every point z, we have an element of G. G is just a map from T to T, so we can compose pi to the right with an element of G, right? Pi is a map from T to D prime, so we can compose to the right with a map from T to T, okay? So this always has a meaning. And so we want that if we define pi z like this, okay, so pi z is just defined as the pi composed with fz. So if we define it like this, so then we want this to have the property that if we take any of these little symbols a, and we look at this distribution, and now we test this distribution against the test function, which is like the test function we used in the definition of the C alpha spaces, right? So you just take a smooth, compactly supported test function, and you rescale it by lambda horizontally and sort of lambda square in time because of parabolic scaling, and then by whatever it takes vertically so that the integral doesn't change. Okay, and then you recenter it so that it's centered around the point z. Okay? And then you test it against this. Well, and you want this to behave, well, you can guess how it should behave like. It should behave like lambda to the power the degree of this guy. Right? So here you would want lambda to the power degree of A. Okay? And so now this is our space M. So now this space, well, you see so in general, this is not a linear space at all, right? So there's no, so for starters, you cannot add the elements of G, right? So this clearly doesn't have a structure of a linear space because you can't add these elements here. Right, and I mean the pi's in principle you can add them, but then if you add them, it's not clear, right? This would not be satisfied for the sum because you wouldn't have a good definition of the pi z unless you take the same f for both of them somehow.
The collection of all p and z, right?
So the big F, right, so the big F here is just a map from Rd plus 1 into G. Right. And the boldface pi, we said already, is a map from T to distributions. Okay? So now, here, so this condition here gives you an enormous amount of rigidity in this space. Okay? So actually, if you know, it's not totally trivial that this space is not empty somehow, for example, right? Well, it turns out that it isn't, okay? I mean, so you can show that if you take a smooth noise and you actually lift it in sort of the canonical way, so you sort of define the boldface pi by these kind of formulas, then, you know, there exists a unique F which makes this true, and so this defines uniquely an element of that space. Okay? So at least there are some elements in that space. And now you want to, you know, you want to show that these things actually you can take limits. So there's a natural topology in this space, right? So there's kind of like a norm, which is basically the best constant you can put here, right? So this gives you, so it almost behaves a bit like a linear space, right? It's almost like a Banach space. You have something like a norm on it. You have something like a distance, right? So there's basically a natural way of building a distance, which is, well, essentially if you have two guys like this, well, at this level you can always just add them or subtract them, right? And then look at the best constants for the difference. And, well, this essentially already gives you a topology on this space. It has a number of sort of non-trivial properties. Okay, so for example, there's a highly non-trivial fact here, which is, for example, that if you take, right, so I can define a gamma. So if I define gamma z0, z1 to be f z0 inverse composed with f z1. Right, so then if I define the gamma like that, then it has the property of the gammas we already saw yesterday. Right, so that pi z0 times gamma z0 z1 is equal to pi z1. Right, simply, you know, if I multiply this with my gamma, the f z0s just cancel each other out, and the z0 turns into a z1, right? So it's clear that you have this identity here. It's not clear what sort of, you know, if this should sort of satisfy any bounds or anything. But it turns out that actually just from these definitions, and here it's very important that you have, you know, there are lots of restrictions here on what the f is allowed to be. So it's not allowed to be an arbitrary linear map from T to T. It has to be a linear map of that form, right? So that gives you a lot of rigidity. So if you define the gamma like this, then it turns out that if you take gamma z not z1 and you apply it to some, you know, any of the basis elements of your space, and then you look at, right, so now that gives you again, so gamma is a map from T to T. You apply it to an element of T, you get a new element of T. So now you look at the component of, say that guy has degree alpha. And so here you look at the component of degree beta, say. Okay, so it's an element of T. So it has components in front of each of these guys. you take a guy of degree beta, you look at the component that's in front of that guy. Then I claim that this is automatically bounded by something of order z0 minus z1 to the power alpha minus beta, actually. Okay, and that it's actually 0. Okay, so it's this if beta is less than alpha and 0 otherwise. Okay, yeah.
There's a point that I'm missing, maybe not one, but in your M, then you've got this evaluation map that takes symbols and spits out distributions. But in your diagram, you said that you have distinguished the probability part, which gives meaning to the regularized noise. But then I don't understand, because there, if you give a symbol, you give a distribution, you need to have a notion of regularize.
Right. So, okay. So at this stage, this is a purely analytical definition, right? So at this stage, there's no probability here whatsoever. Right? You just say, okay, so I have this space. It's some sort of weird space of distributions somehow, right? And that's it. So now the probability part would be, well, so if I take a regularized noise, I have a canonical way of building a regularized pi for it. Right? So there's a canonical way of taking a noise and building a pi by a formula like that.
So it's choosing an element of M.
It chooses it gives me a random element of M, basically. Okay.
Okay.
So a random. So if you take, it's choosing a random element of M. Okay. So you basically end up building a probability measure on M in the end, right? And so your regularized noise certainly does give you a probability measure on M simply by that formula. And by the claim that I made that if you define a pi like that for a regularized noise, there's a unique choice of f that goes with it, and it actually belongs to it. Okay?
May have maybe more choice.
And not right. So the thing is that in general, not every element of M is a limit of things like that. Okay? So in this, so it depends a little bit on the structure. So for example, this theory of rough paths is a special case, so you can actually interpret it you can build it in exactly that way. And in that particular case, you can actually show that every guy is obtained as, or actually, well, so they seem to just look at basically the subspace, which is of the closure of everything you obtain by taking a smooth function, lifting it to the space, and then you get some subset of the space and you take the closure of that set. Okay? So here in general, if you take a smooth guy, you lift it here, and then you act with this map, that's going to kick you out of the range of that map. Okay? So the range of this map here is not at all preserved under this action. Okay? And it's not even approximately. Okay, so it kicks you out of the closure of the range in general. Okay, so it's not true. So here it's not true that you can get away with simply taking smooth things, lifting them, and take the closure of smooth stuff in here. Right? That's too small.
So if you stay in the line downstairs, that by regularizing the noise, applying the good element R on F, and then getting a function, you won't get the full answer.
Oh no, you do, because you act on R. But it means that you cannot simulate the action of R by just adding some weird oscillations to the noise that have some effect of simulating this, right? Whereas in some cases you do, right? So if you take a stochastic differential equation, right? So if you have a bunch of vector fields that drive a differential equation, then you can, for example, simulate the addition of any Lie bracket of these vector fields by adding, some kind of oscillations to your noise, right? So if you add some sort of spiraling oscillation to the noise, that gives you approximately an additional term that pushes you in the direction of the Lie bracket, right? And if you take the actual limit of this, right, you would hear the noise itself would somehow, the oscillation would vanish if you just take you know, if you just test against test function or something, as in the sense of distribution, that would vanish. But in this sense, the effect would not vanish, and that would sort of emulate, if you want, right, the action of R on this. Right? So in the sense, right? So, but in general, you cannot. So, for example, you cannot emulate the Ito-Stratonovich correction, right, by adding weird oscillations. Right? Because the only thing that you can emulate is basically iterated Lie brackets, and the Ito-Stratonovich correction is not of the form of an iterated Lie bracket. Right? So even in the usual sort of stochastic differential equation case, there are elements in here that cannot be emulated by just adding weird oscillations to the driving noise. Right? Okay. Right. So the fact that you get 0 here is sort of trivial because you can just see that this is a property which is preserved by all these operations. So a map of that type only ever creates things of lower degree because okay, I didn't say this. So here you would go with degree less than the degree of A. Okay, so there's a condition that here you actually only lower the degree, actually degree of I of A. Sorry. So there's a condition here that you lower the degree, and this condition sort of propagates by these assumptions. So this is somehow trivial, but this is highly non-trivial, right? So it's not obvious why this would be the case, why a bound like this would be true. It turns out that it follows from this fact here, so it would not be true if you didn't impose this, and well, sort of follows from the whole structure, and it's some form. Actually, it follows from an analysis which is somewhat similar to how you prove the Schauder estimates in the usual case. So this is some form of sort of an echo of a Schauder estimate somewhere.
One more
yeah.
question. So you say that this M is usually non-empty because you can get regularization of your noise
right.
to M, but is it that clear that it's not an enormous space?
Yes, because you can basically, right, you can essentially characterize how big it is in some sense. And in some sense it is, in a way you can parameterize the space M by basically one function for each guy of negative degree. Okay, so there's kind of 1 degree of freedom for each guy of negative degree, and then the guys of positive degree, the whole structure here is sufficiently rigid that the guys of positive degree are uniquely determined by the guys of negative degree. Okay, so you know exactly, in that sense, you know exactly how big it is. And even the guys of negative degree are sort of partially determined by the other things. So you can really parameterize that space M by having, for each guy of negative degree, you have a function of order C alpha for exactly alpha given by the degree of that guy. And it's parameterized by that, but there's not a canonical parameterization by this. Okay, so there is a way of parameterizing that by that, but that parameterization involves a choice. Okay, and there is no canonical choice. There's no way of doing this in a canonical way, and therefore that's why you don't want to. And furthermore, the topology isn't really that topology either somehow, right? You can parameterize it by that, but it's somehow not the right way of looking at the space. But it tells you how big it is in a rather precise way. Yeah. And that's actually also somehow what tells you, right? That somehow tells you how much freedom you would expect to have in here, right? Because of course it cannot. It means that this group here, the action of that group, has to preserve, you know, this kind of structure which determines the guys of higher degree in terms of the guys of lower degree, right? And so you have to find an action here which somehow preserves that structure. If it kicks you out of that, that means it wouldn't preserve the space M. Right? So the non-trivial bit here when you construct this group is to show that the action that you get actually preserves that space in the sense that these bounds are still satisfied. And that the action is actually a continuous action. So it gives you, it acts by continuous maps on the space M. Okay, so, right, so now remember, yesterday I gave you a definition. So I said if you have these gammas, right, and you have the bold-faced pi, then that actually allows you to define a space, say, D gamma, which is really the analog of the space of usual Holder continuous functions. And so that was simply the set of all functions, say, h from Rd plus 1 to t. Right? So now what we're looking at is basically sort of like at every point we give ourselves a bunch of coefficients of something like a Taylor expansion, and that's how we should think of also differential, but also the usual C gamma function. I showed you yesterday how you think of them in terms of coefficients of a Taylor expansion, and then you just have a natural norm on these coefficients which is equivalent to the usual C gamma norm. And this norm was given by, well, what you do is you just look at h of, say, z1, you compare it to z0, you compare it to gamma z0, z1, h of z1, and then you look at the component of degree, say, beta, and then you want this to be bounded by z1 minus z0 to the power gamma minus beta. And of course, the natural thing here is to also impose that this guy, really doesn't have coefficients of degree bigger than gamma, in the same sense that, if you take a C3 function, it doesn't make any sense of giving yourself somehow a fourth order Taylor expansion at every point, because it just doesn't have a fourth derivative. So there's no point in trying to even define one, right? So here it's natural to just look at things of degree less than gamma. Okay, so now we have our Holder spaces.
Is it clear that it corresponds to something? I mean, that there is a distribution behind this or a function behind it?
That's a very good question. Right? So that's now one of the somehow main theorems or main little fundamental theorems of this whole business, is that now if gamma is positive, okay, so then there exists a unique distribution, say, RH in D prime, right? So if gamma is positive and H is in D gamma, okay, so then there exists a unique distribution, which I'm going to call RH, which has the property, well, that it is really the distribution behind H, okay? And in the following sense, well, what you want to do is you want to take RH, which is a distribution, and given the point Z, you want to actually compare it to its Taylor expansion around the point Z. Right? So what is its Taylor expansion around the point Z? Well, it has coefficients H of Z, and the way you turn coefficients at a point into the actual distribution, well, that's this pi z guy, right? So you just take the pi z guy. Now, this is a distribution, right? So pi z is a linear map from T into distributions. This is a distribution. I can subtract the two distributions. And then, well, I want to sort of say that this is small near the point z. Since it's distributions, again, I'm not allowed to evaluate at points. The only thing I can do is test against test functions. So again, I test against one of these, rescaled, recentered test functions. And then the natural thing is to say, well, if this guy is, C gamma, well, it means that this, comparing it to its Taylor expansion should give you an error which is at most of order gamma. And so here you would want to have lambda to the gamma. Right?
just to be sure that I understood, this theorem works for any fixed guy in M, right? You fixed pi and f in M.
Exactly, yes. So, exactly. But you also have continuity. So the map, right? So this map here now is really it's not just a map from d gamma into distribution. It's really sort of a map from d gamma times M, except that you can't really. It's not a product space, right? Because the definition of the space d gamma itself depends on the element of M you're considering, right? Because it depends on these gammas, and these gammas were defined from the Fs, and the Fs were actually the Fs that are in your element of M, right? So in some sense, what you have is really something that looks more like a kind of vector bundle, right? So you have a, okay, so I have to erase something now. Okay, I think I'm going to erase this because that's not so important. Oops. Right, so the picture now is the following. So we have our space M here, which is not a linear space, okay, because we have these kind of nonlinear constraints and things. And then for every point in M, okay, so a point here would be sort of this pair. For every point here, we have a vector space, which is the d gamma. Right, it's actually a Banach space. Okay, so we have the d gamma corresponding to that point, right? So you have a different d gamma at every point because the definition depends on your element of M. And now, so you have a topology on M, you have a topology on these guys, and so you actually also have a topology really on these. Right, so there's a way of comparing a guy here to a guy here, and it's basically given by take this expression for the first guy, take the corresponding expression for the second guy with its own gamma, and you subtract the two, and you look at the smallest constant here, right? So there's a very natural way of actually comparing guys that don't sit in the same space. And so now this map R is really a map from this whole bundle, okay, into distributions, and it's really continuous as a map on this whole bundle and not just on each of the fibers. Okay. There's another thing I want to mention, which is that, okay, so this is sort of very appealing. So this looks very much like a sort of usual kind of a vector bundle. Technically speaking, it's not a vector bundle. Okay, because these spaces, these d gamma spaces, are not actually isomorphic in general for different elements of M. Okay, so that's sort of one of the features of this whole business, is that actually, even though you just define it like this, and you have the impression that, well, the specific choice of this gamma doesn't really matter too much in this definition. If you think about it in specific cases, and I'm going to give you an example in a second, the space d gamma, they can look very, very different for different choices of an element of M. Okay, so they can really look completely different. And they look different, I mean, even in the sense that, every neighborhood in here will have different d gammas that are not isomorphic, right? So there's no point in which you can actually turn this into a nice vector bundle. Okay, and so let me just give you a very simple, and this is a very general theorem, right? So this is not specific, it uses actually very weak information. Okay, it sort of uses the type of information that I just gave you. It doesn't use anything specifically about stochastic PDEs or about this being a heat kernel or something, right? I mean, it uses relatively weak information about knowing how these things blow up at the origin. But it's so this is somehow really a very general fact. Okay, and it doesn't even, yeah, I mean, there's the actual formulation of this theorem doesn't even make use of, you know, information about convolutions and things like that. And I mean, it's actually more general than that. So this is really a very general fact. So let me just give you this example. So if we consider the simplest case, where here we basically stop here, right? So we look at, so all we do is we only keep this guy and this guy here and nothing else, right? So that was somehow our first guess yesterday, is to say, well, you know, to very first order, these solutions locally should look like a linear combination of this guy here. So let's just keep these two guys and nothing else. Okay, and so you have a, so now I have a h of z, which is of the form, say, h of z times 1 plus, well, let's call it h prime of z, but it's of course not a derivative, but it is some sort of higher order information times that. Okay. And so now what does it mean to belong to d gamma, right? So how does our gamma act on this space, right? So this we actually saw yesterday already. So gamma applied to this was actually just something like this guy itself, and then plus v of z1 minus v of z0 times 1, where v is, you know, again, sort of the same v that appears here, okay? And maybe the sign is wrong again, okay? And so now, what does it therefore now mean that h is in this d gamma space, okay? Well, it means basically as before, so it means that h prime of z1 minus h prime of z, so h is in d gamma if and only if h prime of z minus h prime of z0 is basically of order z1 minus z0 to the power gamma minus the degree of that one, right? But the degree of that one is not 1, it's a half. So here you have actually gamma minus a half. Okay, so it looks very much like the usual Hölder continuity, but in the usual Hölder continuity here we had a 1, right? So your C gamma, if your derivative is C gamma minus 1, here your C gamma, if your derivative is C gamma minus a half. And the value itself had to satisfy h of z1 minus h of z0 minus h prime of z0 times v of z1 minus v of z0, or the z1 minus z0 to the gamma. Right, so it basically looks like the usual notion of Hölder continuity. The only difference is that here, instead of comparing to a linear function, we're comparing to an increment of v. And here, instead of imposing that the derivative is C gamma, we impose that it's C gamma minus a half. Okay. And so now take, take now gamma somewhere, so what do I want to do? Right, so I take some gamma which is somewhere between a half and 1. Okay? So I take gamma somewhere between a half and 1. And then, now look at what's somehow the structure of this space D gamma. Right? So first, in order to, to really be in M, basically you want the V itself. There's some condition on the V itself, which is given by this topology which was erased here. But then basically that condition tells you that the V itself has to be Hölder half, right? I mean, it has to behave in a way which is kind of compatible with that exponent here. So V has to be in C1/2. Okay. So for example, so say that your space is one-dimensional. Okay, so now V is just a function of one variable. So for example, I could take it a typical sample of a stochastic process. So here, if I put things equal to really a half, I'm not really allowed to take Brownian motion here because Brownian motion is not in C1/2. So I could either change C1/2 into 1/2 minus a little bit, or I could take, for example, a realization of a fractional Brownian motion with Hurst parameter just a bit less than a half, or something like that. Okay, it doesn't really matter. I can do one of the two things. And then it turns out that if you look at this bound here, if you take here something like a Brownian motion also, and so a Brownian motion is not just Hölder, well, basically a half. It's also effectively sort of Hölder half from below. Okay, so it's really at it doesn't really behave better than Hölder half at any point, right? And so if you want to have a bound like this, okay, so and the gamma here is really strictly bigger than a half. So if the V is a typical realization of something like a Brownian motion also, you can see that given H, there can be at most one choice of H prime so that this is satisfied. Right? So exactly like in the case of usual C gamma spaces where the derivative of a function is uniquely determined by the fact that if you compare the function to its first order Taylor expansion, the error is sufficiently small. Right? That uniquely determines the derivative. And here it's exactly the same thing. If I take here something like a realization of a Brownian motion also, then the H itself uniquely determines its derivative via this bound. Because if you modified the derivative a little bit, then well, this is sufficiently big so that it would actually break that bound, right? So of course, there might be some H's that in a way don't have a derivative, just like in the usual case, there are functions that are just not C1 and they don't have a derivative. But if it has one, then it's unique. Yeah. Okay? On the other hand, of course, being in C1/2 doesn't prevent you from actually being smooth. Right? So I mean, the function 0 is also in C1/2. Okay? Now if V is 0, then this just disappears. Okay? And then all this is saying is that, well, H of Z minus H of Z0 should be equal to this. Well, if gamma is less than 1, there are lots of functions that satisfy this. Right? So then it just says that H has to be a C gamma function. And then it just says H prime has to be a C gamma minus a half function. And they're completely independent. Right? So you can choose H and H prime as you want. Right? And of course, if you take, and that's also true if you take for V basically any smooth function. Right? So if you take any smooth function here, it doesn't really matter what H prime is. Now, of course, if you take a non-zero function, then different choices of H prime would somehow change your norm here. It would sort of affect the value of the constant here, but it wouldn't affect the fact that this bound is satisfied, right? And so you see that if you take for V typical realization of a Brownian motion or something like this, then H prime, then this d gamma, the corresponding d gamma guy, has the property that H uniquely determines H prime. But if you take any smooth approximation of your Brownian motion, then H and H prime are completely independent, right? And of course, for a given realization, there are lots of smooth approximations that are arbitrarily close. Right? So that's what I meant earlier on when I said that, it really doesn't look like a vector bundle anywhere here, right? In the sense that these spaces are really not isomorphic. So here clearly the guy with V smooth and the guy with V typical realization of Brownian motion, they are certainly not isomorphic. One of them is basically described by two independent functions. The other one is described by one function which has a very specific behavior somewhere. Right? Okay. So, right.
What's the condition that it uniquely determines?
Sorry?
So you can give so one can give a condition that it uniquely determines function H prime?
Yeah, well, okay, so okay, yeah. So in this specific case, so in this sort of simple case, you can give a definition. So yeah, so we have, so there's a paper with Natash Pillai where we, well, so we prove a Hellman's theorem for fractional Brownian motion, but in the proof of Hellman's theorem, you need Norris lemma, and in Norris lemma, you want something like a Dubh-Meyer decomposition, which is sort of quantitative, okay? And in some sense, the Dubh-Meyer decomposition is really the sort of uniqueness of Dubh-Meyer is really H prime being determined by H, okay? So this is, so if you think, it's really the same thing, right? So if V is a Brownian motion, and H is something like a stochastic integral, right, with respect to your Brownian motion, then the H prime would be the integrand of your stochastic integral, right? And Dubh-Meyer, and so if you have a semi-martingale, well, it's a nice bit plus a stochastic integral, right? So then this bit just extracts the integrand, therefore it basically extracts the martingale part. So the fact that H prime is uniquely determined by H here is sort of the analog of the Dubh-Meyer decomposition, okay? The uniqueness of the Dubh-Meyer decomposition. And so in fractional Brownian motion, you don't have Dubh-Meyer decomposition, but you still have this, okay? And so we can prove, for example, we did prove that for fractional Brownian motion, you do have this H prime uniquely determines H. And the way we prove it is you give a specific analytical condition. So it's something like, it's an analytic, so you give an analytic condition, which is essentially something like, so we call it Holder roughness, right? So it's sort of like Holder regularity, but from below instead of above. It oscillates somehow sufficiently at every scale. Okay, you have to be a little bit careful with how you set up the definitions, because of course oscillations sort of every now and then you get, you know, the difference is actually zero because you sort of oscillate like that, right? And so you have to actually set up the definition in the right way, but it's not very difficult to do. And then you can quantify this, right? So you can give a sort of modulus of Holder roughness, which is sort of like a roughness from below, right? And then you can quantify this uniqueness in the sense that you can show that like H prime is smaller than, you know, sort of like, you know, and in terms of that modulus of roughness, and then you can just separately by some chaining argument, you can show that the modulus of Holder roughness for fractional Brownian motion is finite. I mean, it's non-zero. You can get kind of tail estimates. Okay. So, right, so now, you see, so now we have almost all the ingredients, right? So how do you now set up, right, this solution map, right? So now you want to say, oh, I take any guy in here, I want to use that to actually build something like a solution map, right? So, you still, right, of course, this is a separate one, yeah, but so this, unfortunately, you won't be here tomorrow, so. Right, so at the moment, so today is completely sort of analytical question, okay, so it's somehow just building that solution map. And then, of course, there's the separate probabilistic question, which is, you know, well, so what is that group R, which is sort of part of the algebra bit, and then this. Okay. Now you see, so if we take an H, which is of the form, you know, little h times 1 plus, you know, I don't know, so say h, well, let me just write it as a sum of HAs times A, right? So you take just a guy like that, which is in D gamma. So now the first thing we want to do is we want to sort of, you know, we want to give a meaning to this equation, which was erased now. And so we want to actually have a meaning for the right-hand side of the equation. Right? Well, it's more or less clear, right? So so you have h. So what would be the derivative of h? Well, derivative is a sort of local operation, right? And so the Taylor expansion of a derivative is just the derivative of the Taylor expansion, right? And so basically what it means is that, well, the zero guy disappears, and then all you do is you sort of keep the same guys here, but here you replace A by, in a way, dA. Right? And what is dA? Well, it's just whenever you have a guy which looks like this. Right? Whenever you have a guy which is of the form heat kernel convolved with something, well, then the derivative of that guy should be derivative of the heat kernel convolved with that. Right? So it should be this guy here. Right? And the thing is, you expect, in this expansion, you expect to have only guys of that form appearing, right? Because the equation itself is an integral. You can rewrite it as an integral equation, and so it's H equal to heat kernel convolved with the nonlinear part of the equation. Right? And so in the expansion of H itself, you actually have only guys like this appearing. Well, maybe you have x's appearing also. Right? So you had the x appearing, but then of course the derivative of x, we know what it is. It's just 1. Right? Okay, so here you only have guys of this type and of this type appearing. And so I know what their derivatives are. It's sort of these guys here. And so I have a natural candidate for this. Okay? And you can show that if H is in d gamma, then, well, its derivative is in d gamma minus 1, as you'd expect. Okay? And this is actually still true here. And it's relatively easy to check. Now, we also have a product. Right? At least we have a partial product. So we know how to multiply these things. And again, if you think of Taylor expansion, the Taylor expansion, it's a local operation. So the Taylor expansion of a product is just the product of the Taylor expansions. And then maybe you truncate it or something, right? But it's basically just product of Taylor expansions. And so we do have a, right? So we know what this is. Okay, we know what this is because it's just the product of the Taylor expansion. So it's just the sum of HA, HB times dA, dB. And now here, well, it turns out that, well, okay, so now it's not clear whether this, of course I can do that formally, but it's not clear at all how it actually, plays with my definition of these d-gamma spaces. But then on the other hand, you've all seen somehow, you've all proven in your undergraduate days that the product of two differential functions is differentiable, and you can basically take that proof and do exactly the same thing, and you conclude from that proof that the product here, well, what should it be in? So if it were usual Hölder functions, the product of two Hölder functions has the sort of the minimum of the two regularities. Here that's not quite true. You actually lose a bit more. And the reason why you lose a bit more is because here you have things of negative degree showing up. Okay? And then if you have something of negative degree, in some sense it behaves a bit like a differentiation operator of that degree. And so here, the thing of lowest degree appearing is a half, right? Because the guy of lowest degree in here was actually this one, which was of degree a half. And so now since differentiation decreases degree by 1, here the degree is going to be basically bigger than minus a half. So there's going to be things of degree minus a half here. So in some sense, dH acts also a little bit like a differentiation operator of order a half, of order minus a half, sort of onto itself. And so it's not unreasonable to think that here you would actually not be in d gamma minus 1, but actually in d gamma minus 3 half. So you kind of lose a half derivative, which comes from this minus a half here. Okay? And okay, one can check it again, and it's not very difficult to check.
You can check that purely formally by your...
Purely, just using that definition and using this definition and this fact. Okay, so this is very important here. But otherwise it wouldn't be true. But if you combine these two, it's a it's a 3-line calculation, so it's really not difficult. So this is very easy to check. Yeah? Then what else did we have in our right-hand side, right? So we had h itself, we had derivative of h, we had the noise, but the noise we have a little symbol, and so we know also what it means to multiply by the noise. We just multiply the symbol by these things. That's not a problem. Then we have actually nonlinear functions of h. Okay, so we had nonlinear functions of h. So how do we define a nonlinear function of h here? Right, so we had things like sigma of h. Right, so what should be the correct definition of sigma of h? Well, h is of the form its value and then plus stuff, but this is all just higher order information, right? It just tells you how things behave locally. So in some sense you should treat this as kind of infinitesimals. Okay, and so the natural thing here is to say that sigma of h by definition should just be sigma of little h times 1, and then if I call this whole thing sort of h tilde, okay, now h tilde is an element of t, little h is a real valued function, okay, but this includes the symbol itself, okay, so this is an element of t. And so the natural thing here is to just take, essentially formally, a kind of Taylor expansion where you put here just the h tilde to the power k. Okay, so you treat the h tilde as an infinitesimal, and you say, well, treating h tilde as an infinitesimal, it's reasonable to define sigma of h like this, and then maybe you truncate somewhere. Okay, so you stop the expansion somewhere here. So this is evaluated at h, right? And this here has a meaning, right? So this here really means h tilde multiplied with itself k times, and we have a product in our space, right? So it is the product in T here that appears. Okay. And then again, you can actually show that it's a little bit trickier to show, but you know, again, so this is maybe a one-page calculation instead of a one-line calculation, but you can show that this is again in D gamma. Okay, if H is in D gamma. So these spaces just behave in the way that you would expect Holder spaces to behave, right? And then, well, in order to set up a fixed point argument, well, the thing that you want to do now is you want to actually be able to convolve something like that with the heat kernel, right? So now we have given an H in D gamma, we basically know how to give a meaning to the right-hand side of the equation, right? Because we know what sigma of H is, we know what these gamma, alpha, beta, gamma of H's are in the same definition, we know what the derivative is, we know the derivative square, we can multiply all of these things. So we can actually just formally have an expression for the right-hand side of our PDE. Right? And we know that the right-hand side of our PDE is going to be, well, it's basically going to be in D gamma minus 3/2, right? Because so here, this guy is in D gamma minus 3/2. And then there's going to be the sigma of H times noise. And that's also going to be in D gamma minus 3/2 because the noise has degree minus 3/2, and it's the same sort of rule that applies as here, which says that it basically lowers the regularity by 3/2, right? So the right-hand side now is in D gamma minus 3/2. So as long as gamma is, right, so the right-hand side belongs to D gamma minus 3/2. And so now we go back to this theorem, right? So which says that if you have an element of a D gamma with positive gamma, then it does really represent an actual distribution, right? So it means that if gamma is strictly bigger than 3/2, and that's why yesterday when I wrote this long formal expansion on the blackboard, I stopped at 3/2, right? So that was this 3/2 here. So if gamma is bigger than 3/2, then this element here does actually represent an actual distribution by this theorem, right? And so then you can basically set up a fixed point argument, right? Because you say, well, I have a candidate solution, which is an element of D gamma. That gives me a candidate right-hand side for the equation, which is an element of D gamma minus 3/2. That gives me an actual distribution, which really represents the right-hand side. And then I can take the convolution of that distribution with the heat kernel. So the distribution is then actually in C it's in C minus 3/2. Okay, so R applied to the right-hand side is going to be in the usual Hilbert space minus 3/2, not gamma minus 3/2, okay, just minus 3/2, and that's because, you know, it's not going to be any better than the noise itself, and the noise had regularity minus 3/2, right? So we have this candidate for the right-hand side. Now we can convolve this with the heat kernel. That gives us a, right, so R of the right-hand side. So that gives us a function which is in C1/2, basically. But now we're sort of stuck, because what we would like is actually have a candidate which is in some D space, not in just the usual C space. But actually you can prove that if the right-hand side is in D gamma minus 1/2, then there exists an element of D, well, gamma minus 2/2 plus 2, so D gamma plus 1/2, which represents this guy here. Okay, and that's a non-trivial fact. Okay, so actually, so theorem, there exists an element, I don't know, say, I don't know, H tilde, which is in D gamma plus 1/2, such that R of H tilde is the candidate for the right-hand side of the equation, okay? And so now we've closed the fixed point problem. Okay, so this is a non-trivial fact, and you have to prove that. But okay, you can prove this. And so now we see that, you know, so we start with a candidate in D gamma. We build the right-hand side, it's in D gamma minus 3/2. Then we look at the actual distribution that this represents. We convolve that with the heat kernel. And we say, oh, now there is actually a guy which is in D gamma plus 1/2, which represents this guy. And so that's our new candidate. But you see now we've actually gained some regularity. And so first, this is a well-posed fixed point problem now. Okay, so it actually, you even improve. You go from D gamma to D gamma plus 1/2, right? And then there's, you know, the usual sort of tricks that if you gain regularity, you can trade gain of regularity for smallness by looking at short times or something, right? I mean, that's sort of the usual type of PDE tricks to show that this now has actually a unique solution for short times. Okay, and so that allows you to, that's how you build this map. Okay, and so now the thing that remains to show is, well, the rest of the picture now is to show that, you know, is to understand a little bit this renormalization. Okay, and so that's what I'm going to talk about tomorrow. Okay.